measures of position. It's just as important to know where a data point is located within a data set as it is to know the central values of a data set and the spread of a data set. However, you need to know those first two things, the central value and the spread, in order to know relative position. All right, so what we're going to do is explore something called the empirical rule and then get into this concept called a z-score, which will give a relative standing, a comparative value that is flexible enough to be used in multiple data sets. All right, so when you're thinking in terms of comparing multiple data sets, so like let's say, for example, you have, well, I have some overlap in terms of students. I have some students who are in my calculus class and my stat class, and you want to know what your relative standing is in one compared to the other. Let's say you get a 90 in one. Let's say you get a 90 in both of them, but you want to know how good a 90 is. All right, because a 90 could be well above average, but it could be also below average if everybody else has a 95. You know, now in the end, an A is an A, so you're not going to be complaining too much, but if you're behind the curve, you know that there's room for growth. You know, if you find that you're one standard deviation below the mean, then you would be thinking, oh, okay, so if I could get up to the average for the class, then I could get as high as a 95 or a 98 or whatever. All right? But if it turns out that your 90 puts you well above average, then your room for growth is a little bit more limited because maybe it's just a harder class. You know, so that's one of the applications of what we're going to be talking about. But there are plenty of others, right? Any instance where you would be thinking about the same variable but different groups of measures of relative standing or measures of position would be applicable. All right. So you might remember this from years past. It's the 68, 95, 99.7 rule. All right. It's called the empirical rule. So if you have a distribution of data that follows what we would call a normal distribution, with my shaky handwriting, it would be centered around the mean. All right, we would call that center value x bar. All right, so this is a normal distribution. All right, if we deviate from the mean by one standard deviation, all right, and that's going to vary from data set to data set. All right, so if I deviate by one standard deviation, I would be increasing my mean by x bar plus 1s, and I would be decreasing my mean by x bar minus 1s. All right, what's going to happen is, if it is a normal distribution, about 68% of the data will lie within that interval. All right. If I go out two standard deviations, so x bar plus 2s and x bar minus 2s, I'd be looking at about, let me get a better line there, about 95% of the data. And if I go out three standard deviations, oh, guess I got to put the 3 in there. Just for the sake of room here, I'll extend it up a little higher. We would be accounting for about 99.7% of the data. So the converse would be true in the sense that if these percentages hold up in a distribution of data, then we could say that that data set is approximately normally distributed. All right. Oh, the more I look at this, the more I realize it looks like garbage. I'll probably import a typed image in later on or something. But what we have here, everything looks better from far away, is a raw data set, from that raw data set, we can compute the mean and the standard deviation, which means that we could come up with those intervals. If we come up with those intervals, then we can make a determination of how many values fall within those intervals, which would give us a sense of the percentages, which in turn, my hook fell, which in turn would give us a sense or an idea of whether or not we're dealing with a normal distribution. All right. So it's a lot easier to do frequency distributions on a TI calculator than it is on Desmos. So I'm going to go with that. I'll put it right here. So I'm going to go stat edit. Question? Say it again? Give or take 2 percentage points. All right, so as long as you're within the neighborhood, so within 2% on the high or low side, you will have met the requirement. All right, so let me put in these values: 14, 16. It's not a lengthy set, so I won't use like shortcuts like a sequence or anything like that to get it in there. It's just typing it in. One, 7, 14, 13, 5. Oh, it had the 5 and a 1. All right. So we get the mean and standard deviation. So I quit out of here. Get rid of this stuff. Stat, calc, L1, L2. All right, because it's frequency distribution. If it was not a frequency distribution, if it's just a raw list of data, then you'd wipe out the L2. You just hit clear on that, but it's not the case here. So I'm going to grab my X bar. Approximately 18.829. And the S, denoted as SX in the calculator, just because it's indicating that it's the standard deviation of the random variable X. All right, this X. That's the default. 2.144 approximately. All right. So in the TI, I'd run the computations, first computing X bar plus or minus 1S, then X bar plus or minus 2S, if necessary. Because it's got to pass all 3 parts of the test in order to be considered a normal distribution. So if I fail the first part of the test, then I don't move on to the second or third. All right. So you kind of, as a student, you're sort of rooting for failure. Maybe that's the only instance where you're ever rooting for failure. All right, so let me show you how you can do these computations pretty quickly and easily in your calculator. I'll say quickly and somewhat easily, because TIs are TIs. You know, like there's built-in language. Once you understand it, it's a lot easier. But until you get a handle on it, it's not quite as easy. All right. So I showed you this a little bit, but let's go through it in more detail. So second, oh, sorry, not second. Forget I said that. Just vars, option 5. All right. Vars option 5 will give you the notation X and SX. I'm sorry, X bar and SX. All right. After you run StatCalc 1, it will have stored the values of the mean and standard deviation in their purest form in for X bar and SX. So it's annoying, but I'll hit option 2 or scroll down to the number 2 and hit enter. I'll type in minus 1 times, then I'll go to vars option 5, scroll down to option 3 or just hit the number 3, it doesn't matter, and hit enter. Run this computation, you have the low bound of your interval, all right, which you can then round to 3 significant digits, 16.686. All right. Once you do that computation once, it gets a lot easier because you can just hit second enter. I like second enter. You could scroll up and hit enter, but I feel like it's extra keystrokes. Second enter, go back and make the minus into a plus. 20.973. All right, it's not an algebra class, so you don't need to show to work in terms of how you got those intervals, or how you will get these intervals. You need to show the mean and the standard deviation, and then show the intervals, and you're good. All right. So second enter, back to a minus, so -2 instead of +1, so 14.542. Now this might not be relevant. I'm showing it anyway though, just so you get the skill down. Second enter, change the minus to a plus, 23.117. Second enter, plus to a minus, 2 to a 3, 12.398. Second enter, minus to a plus, 25.260 is what it would round to. If you do it this way, you don't have to worry about any issues that might emerge due to rounding. All right. So if you take the rounded answers for the mean and the standard deviation, even though you rounded those correctly, it might introduce an unacceptable amount of error in the intervals that we come up with. And if that's the case, then you could end up drawing the incorrect conclusion. All right. So now that we have these intervals, we need to get some percentages out of this. So what I'll do is I'll look at the first one. The first one says that we need to take into account any value that's between 16.686 and 20.973. So I'd look at my x values and I'd say, all right, is 14 in that interval? No. So ignore it. Is 16 in that interval? No, but not by a whole heck of a lot, but still it's not in that interval. So ignore it. Is 18 in that interval? Yes. So we take the frequencies along with the 18. Because remember, the frequencies tell you how many times the 18 happens, how many times it occurs. All right. 20 falls in that interval, but none of the remaining values fall in that interval. All right. So we have a total of 27 values. All right, 27 values fall in that interval. There's a remainder of, let's say, 9, 14, so total of 41 values. Let me just double check that. 22, 35, 40, 40, yeah. All right, so we just crunch those numbers real quick and see if that percentage is close enough to 68 for us to say that this would have met the first requirement of being a normal distribution. And this, unfortunately, or fortunately, depending on how you look at things, is like the most interesting scenario, because that 65.8 falls in that gray area because it's just beyond 2 percentage points. But if you round it to an actual percent, it's right on those 2%. It's like right at the 2 percentage points. So you could say 65.8%. Or you could round it to 66%. Bottom line is, it's too close to call. All right? That's the thing about statistics. You know, sometimes it isn't just x equals this and you move on. Sometimes it's like, all right, we got some gray area here. Further investigation is required. All right? And so that's what this is telling us. So then we would move on to the second computation and see if it works for that one. All right. So I look at that first x value. Does it fall in that interval? No. 16 does. 18 does. 20 does. 22 does. 24 does not. All right. So here we have a total of 39 values over 41 total. So 39 over 41 in decimal form, about 95%. All right, so 0.95, what do they say it was, 1? So this one checks out. So we're saying about 95%. That's pretty close. I mean, 95.1 is pretty close. 95 is exactly what we're looking for. All right, so we would check the last one. The last one, there's really nothing to do there, because if you look at the interval, the low bound of my interval is less than the lowest number in my set. The highest value in my interval is larger than the highest value in my set. So all of these numbers, every one of these numbers, would fall in this interval. So we're going to get 100% there. All right. So we could say that this is approximately a normal distribution. Therefore, approximately normal distribution. You're never going to say something is exactly a normal distribution, because it won't ever be exactly a normal distribution, right? When you're collecting real data, you'd have to have infinitely many pieces of data in order to be exactly a normal distribution, right? So that's not physically possible. So we would always say something is approximately a normal distribution. So if you're right on the line and you're not sure, you could always say it's close to being approximately a normal distribution. That sounds really, really fuzzy, because you're basically saying it's approximately an approximate normal distribution. You know, it's kind of weird, but that's the gray language that we use in statistics. All right, if you're not sure of something, you just basically say in your write-up, I'm not sure. It's pretty close, but not quite. All right, and so that, unfortunately, is how people can sort of spin statistics to, meet their own agenda. All right. As far as a graph is concerned, there is a way to create a histogram on your calculator, and sometimes that could give you a clue going into a problem as to whether or not you're dealing with a normal distribution. So if you hit second y equals, you see all the different plots here? And you could do a histogram on Desmos too. If like I was saying, or have been saying, pick and choose. You like to do this on Desmos, but this on your calculator. When push comes to shove for the AP, everything will have to be TI calculator. But at least up until that point, you can pick and choose what battles you want to fight with what piece of technology. All right, but I will show you the graph and calculator approach, because why not? So hit enter on option 1. So second y equals, hit enter on option 1. Hit enter to turn the graph on. You'll see an option for a histogram, the one that looks like a histogram. So I hit the down arrow, then the right arrow to get over to the one that looks like a histogram. Now, I've been using this fairly frequently, so mine says L1, L2. Yours may not. If yours doesn't say that, then you would just type in second 1, second 2. Now, you see sometimes, depending on the calculator that you have, it'll sometimes have the alpha lock on. Honestly, I have no idea why. So before you hit any kind of function on the top line of your calculator, hit alpha to get that alpha lock off. And then what I recommend is hitting zoom stat. All right, should make sense. I mean, it is statistics. So if you scroll down at zoom 9, zoom stat, and it'll create a histogram for you. Now, it'll decide on the appropriate domain and range and intervals and all that stuff, but it's a good way to get a nice quick look at the distribution of the graph. And if it looks roughly bell-shaped, then you could be pretty confident that the conclusion that you drew of saying that it's approximately a normal distribution is a fairly accurate conclusion. I mean, that looks like it's roughly bell-shaped. And it's not perfect, but that's why we use this, if my marker wants to work, this symbol here, to say it's not perfect. All right, so we have that wiggle room. All right, so how a data point falls within a normal distribution allows you to use it as a comparative measure from data set to data set. All right, so if you know two data sets are approximately normally distributed, and Foss is on the wrong syllable, then you can do an apples to apples comparison. All right, the only difference would be the standard deviation and the mean. Well, difference is, all right. We reconcile that by computing a z-score, which is the number of standard deviations a data point is away from a mean in its own data set. All right, so if I tell you that I got a score on a test that's 2 standard deviations above average, all right, so whatever the spread measure is of the data set, I got twice that value above average. But then you only got 1 standard deviation above average on your test. Even though we didn't take the same test, I know I did better than you. All right? Even if the final number doesn't jive, you know, I might have got a 75, you might have got a 92, but comparatively I did better. I showed more mastery in my course than you did in yours. All right? So very straightforward example. Michael and Jane are in different math classes. Michael scored a 75 on his test. Jane got a 73 on hers. The mean score in Michael's class was 73 and the standard deviation was 7.2. In Jane's class, the mean was 71 and the standard deviation is 6.3. Which of these two students scored better relative to their classes? So key term there, or key phrase, relative to their classes, because we already know who did better. I mean, nobody's going to be throwing a ticker tape parade over the score that they got, but we do know that Michael did better than Jane. We want to know who did better relative to the rest of the students in the class. So we find the z-score for Michael. So z sub m. And then we'll find the z-score for Jane.
Please excuse interruption.
Z-score for Michael. The x sub I value is an individual data point. The x bar and the s are the averages. So Michael's score was a 75. The mean was a 73. And his standard deviation was a 7.2. Or his class's standard deviation. 73 for Jane, that's what she got. But her class average was a 71. And her class's standard deviation was a 6.3. So in both cases, they scored two points above average, but it's going to bear out differently because of the spread of the data. So for the first one, it's 2 over 7.2. And for the second one, it's 2 over 6.3. All right, so we're looking at about 0.278 and 0.317. So our conclusion here, I mean, it's only a slight difference. It's not, you know, anything otherworldly, but it is enough to say that Jane performed better relative to her class. The one thing I would caution you about is qualifiers. So, you know, people will have a tendency to say things like, Jane performed slightly better relative to her class. You don't need to go down that road unless you're confident about the context of the situation, because, I mean, in this situation, you should be fine. All right, it's grades in a class, so yeah, okay, you know, slightly better. However, if it's something that you're not as familiar with, to say something is a slightly better scenario, that could be dangerous, because if you don't understand the context, you may be looking at something that's a small difference but more substantial than you would think. All right. So then unusual values, any value beyond 2 standard deviations away from the mean. You'll see the alternate notation here, just in the interest of being correct. Mu plus or minus 2 sigma. All right, that's for population means and standard deviations. We're not there yet. All right, so x bar plus or minus 2s is the one that we're working with here, because we haven't talked about populations yet. All right, that'll be more in the second unit. All right. Now, what we discovered here, based off of this idea of a z-score, is that since a z-score represents the number of standard deviations that a data point is away from the mean, x bar plus or minus 2s could also be thought of as any value outside the interval of -2 less than or equal to z less than or equal to +2. All right, so if the z value is in between -2 and +2, then we would say that it's considered a usual value. Anything outside of that would be considered unusual. All right, so when they say given a data set where the mean is 72 and the standard deviation is 4, if we want to find whether 59 is unusual, what we would do is find the z-score for 59. If it's less than -2 or more than +2, then we would say it's an unusual value. So z sub 59 is equal to 59 minus 72 divided by 4. So 59 minus 72, that's what, 13, -13? Oh, so it's not going to be a nice round number, so 59 minus 72, yeah, -13, divided by 4, -3.25. All right, so 59 is unusual because it has a z-score less than -2. All right. Also, another caution, be careful about things like unusually high or unusually low. Just say it's unusual. All right? Unless the question asks you explicitly to state whether it's unusually high or unusually low. Context can be a determining factor when it comes to stuff like that. And it's kind of tricky because I use the analogy, I don't know if it's an analogy, but the relationship between golf scores and basketball scores. All right, if you play basketball, the more points you get, the better you are, right? Like you win the game if you score more points than the other player. In golf, you win the game if your point total is less than your opponent. All right, so if I say something is unusually low, it has a negative connotation. So if I say my golf score is unusually low, the reader might interpret that as you're indicating that there was a poor performance. Although by numbers, you're saying the score was low, the performance was good. All right, so there could be a little incongruity there in terms of what you're expressing and what the reader is interpreting. All right, and when it comes to the AP, you're at the mercy of the interpretation of the reader. So if the question does not explicitly say to determine anything other than whether or not it's unusual, then just leave it at that. Just say it is unusual, period. And I'll tell you, a lot of the explanations that we're going to write in this course, they are not going to feel grammatically correct. All right? You're going to write stuff, you're going to be like, whoa, that does not flow at all. But that's okay. That's to be expected. All right? We're not here for the grammar. We're here to get the point across. And you really have to think about the explanation as being kind of just another way of writing an equation. It's a formulaic approach. All right? So we write explanations a particular way, even if the grammar doesn't feel right. All right? So I'd say that that's probably enough for today. So I'm going to put a star on this problem. I'm going to ask you to have a look at this question on your own, and we'll tackle it together. I know tomorrow, I think tomorrow's their shortened periods, and same thing with Friday. Then Monday we have, there's a peer group thing going on, and all the freshmen are not going to be in, or something along those lines. So if you didn't see the notice, I moved the test from Monday to Tuesday because of all that stuff. So just keep that in mind.